All right, so today we're going to be going over NASA's CEA calculator, chemical equilibrium analysis, the nifty tool we use that does a lot of the difficult math for us. So basically, so what is CEA? So as you know, in a rocket engine, there's combustion of your fuel and oxidizer, which happens at very high temperatures and pressures. And I don't know if you guys remember from AP chemistry, but a lot of these reactions occur it's an equilibrium reaction. So it doesn't always go all the way to completion. There's lots of weird intermediate compounds and stuff. And that's all very difficult to calculate by hand. So NASA made a calculator to do it for us. So yeah, it calculates the combustion reaction chemically, figures out all the thermodynamic, like how much heat comes out of it, what your combustion temperature is going to be. And then it does a bunch of ideal gas relations for us that will help us with the nozzle stuff. Obviously, this is all pretty difficult. Most of you guys are freshmen, and NASA does this for us. We're going to go into this a little bit at the end of the class for those who are curious. But also, if anyone wants to take a deeper look, you can contact me about getting these textbooks and looking at them. But yeah, for now, we have CEA, and it does it for us. So how are we going to use it? So CEA is actually like built for rocket engines. It doesn't just do the combustion analysis. It does it with the application of rocket engines in mind. And basically all of the parameters we had you guys choose last week are the inputs for CEA. That's why we had you guys choose those last week. So we put those in, and it gets us a whole bunch of useful stuff. Like it'll actually give us the ratio of the nozzle throat area to the nozzle exit area. It gives us tons of flow parameters like exit velocity, throat velocity. It gives us thermodynamic parameters. It gives us the chemical composition of the combustion gases. And it gives us a whole bunch of other stuff that we don't actually need. But all of these things above are what are going to be useful to us. So yeah, as I said, everything that we picked last week is going to be an input. There's only one value that we didn't pick last week, and that's the oxidizer to fuel ratio. And the reason we didn't have you pick that is because that's actually best found iteratively using CEA. It's not actually the stoichiometric ratio for some weird reason that has something to do with masses of compounds coming out the back of the engine. I don't actually know the specifics of it, but yeah, the best way to find that is to just put a whole bunch of different fuel and ox ratios and find which one's the most efficient using CEA. And I actually know Sam, who I'm not sure if Sam can make this meeting, but he made some kind of code script that will. Is that Sam?
Yeah, I'm here. I can
cool.
put the script in the Google Drive. It's Python, so you'll have to have that installed, and I'll include a README with it. I'll put that in tonight.
Yeah, I'm not going to show you guys that because I've actually never used it. I guess if you want to try that, just find it in the Google Drive and follow the README. Or if you want, Sam can go over it on Thursday. But I'm going to show you how to find the optimal OF ratio without using that script. His just makes it a little easier to deal with. All right, and with that, I'm just going to go straight into a sample run through, or a few different sample run throughs, because CEA's software is a bit finicky. So I want to do it a few different times with a few different examples, just so that everyone gets a bit familiar. I'm also going to copy and paste the link to this website into the chat, if I can find the chat. It does not give us the length of the combustion chamber. That and the actual specifics of the nozzle dimensions. Oh, that's not it. Are going to be covered next week. Hold on, let me finish. That's not what I wanted to do. Arun's here.
I am.
Control C. There we go. Thanks, Gideon. Yeah, so CEA will not give you any specific dimensions for the engine. That you have to do a little bit of math for, that we're going to cover next week. But yeah, it will give us a lot of other useful stuff. So here's the front page for CEA. It has a whole different types of applications. We're only interested in the rocket one. The others could be pretty interesting if you play around with them. I don't know, but yeah, we're gonna go with rocket. So go ahead and put in whatever that random code that it just wants. And here it brings you to the first page where you put in the chamber pressure that you have. And so the way CEA is set up can kind of be confusing. So over here on the left, what it does is if you want to test a range of values, you can put in the low value, the high value, and then an interval, and it'll do, so let's say you put in like 300 to 500, interval of 100. That'll give you the results for a chamber pressure of 300, 400, and 500 PSI, or whatever units you select down here. Alternatively, you can just enter the values over here on the right. So if you wanted to do that same spread, you could just put in 300, 400, 500. And if for some reason you want to do 550, you could also do that.
Sorry, wasn't the maximum we're allowed to 300?
Yes. Or, I mean, it's kind of flexible. I'm not exactly sure what pressure the tanks were rated to, but
That stands, yeah, I wouldn't
100.
go past 300. The valves are technically rated to 500, but yeah.
The examples I'm going to do are not going to fit to the requirements that you guys are held to. The first one I'm going to do is actually for the regen engine that we just finished designing, just because I have those. And then the other example I'm going to do is the engine Arun and I did over the summer that was ethanol liquid oxygen that I sent you guys the spreadsheet for on Thursday as an example.
Jackson, before we go on, I think we still should explain how to pick pressure a little bit better, like why we're doing this. I know I've been getting questions on that.
Okay, if you want to cover that real quick, I'm not exactly sure what you mean by that.
Like basically like, so chamber pressure tends to, a higher chamber pressure tends to provide more thrust because of the way the expansion works in the nozzle. So generally the higher chamber pressure is desired, but there are drawbacks because that means your nozzle tends to be bigger, and also you need to be able to hold more pressure and supply more pressure, so you end up with more weight is primarily what it is. So as far as what we're doing right here, it's basically to build a spread of pressures so that we can see what the combustion efficiency losses are if we use a lower pressure, because sometimes using a lower pressure, it's still going to save us overall efficiency because we can build with lighter materials or have a cheaper feed system.
Okay, yeah, that is a good explanation of why. And that's the same thing for kind of all of these variables we're picking. CEA lets you do a whole spread of them just to play around and see which ones are the most efficient without having to redo this like 100 different times. You can just test like a bunch of different combinations at the same time. So with that, yeah, I'm going to start with the example of regen. So we had a chamber pressure of 500 PSI gauge. So this is in PSI absolute. So just add atmospheric pressure to that. So it's 514.7 PSI. And then, yeah, down here you can pick your units. There was one set of units, I don't remember which one it was, but over the summer we found there was a bug in the code and converting units on one of these. I think it was the pressure units did the conversion wrong.
Yeah,
So,
I think it was pressure with megapascals.
yeah, interesting. I'm seeing it's not here anymore, so maybe they realized that and took it out. So I would just suggest doing PSI because that's pretty much it's what we've used in the past, and it's everyone kind of has a feel for what a large amount of PSI is, if that makes sense. All right. So with that, we'll move on to selecting.
Does everyone know what a PSI is? Because it's just pounds per square inch.
Yeah.
So atmospheric is 14.7.
Yeah. All right, so now with fuels, CEA gives you a few different common types of fuel, methane, hydrogen, RP1, rocket propellant 1, which is a grade of kerosene, although we aren't quite using RP1. We wanted to make it a little more accurate, so we're going to pick our propellant from the periodic table. So just click on that, hit accept, and then it brings you to the periodic table. And you basically just select whatever elements are in your fuel. So for us, kerosene is a hydrocarbon made of carbon and hydrogen. So just do that and hit accept. And now it gives you all the different hydrocarbons you could ever want. And luckily, it a lot of these are kind of just chemical formulas, but over here you'll see some of them are actually named, which is good for us because I don't actually know what the exact chemical formula is for kerosene, but I do know that what it is that we're using is similar to Jet A fuel, which is just a grade of jet fuel. If you see RP1 is here as well. It's another type of grade of kerosene. So we're going to go with Jet A.
Also, just so you're aware, paraffin is pleb tier kerosene.
Is what?
The poor people kerosene is paraffin.
Yes.
Paraffin is what you get if you heat up kerosene too much and then it deposits on the interior of our cooling channels.
Yeah.
It's actually
shit.
different dialects. Paraffin means different things.
Yeah.
Interesting. All right, so we're going to go ahead and accept that. And we don't want to, it also, I guess, allows you to put a mix of fuels, but we're using pure Jet A for all intents and purposes. Where did that come from? Anyway, so we don't click that box and hit continue. Yeah, so it's the only thing we have So its weight percent is going to be 100%. So just hit accept and continue. And then it asks a whole bunch of other things. Yep. It says you can just leave them blank. Temperature, we're just going to say room temperature. So, oh boy, I'm going to leave that blank because I don't see a units on here. I think it'll just assume room temperature. Anyway, let me shut my phone up. Okay. So for oxidizer, it again uses, or it gives you a whole bunch of common oxidizers. You got, I don't even know what Cl2 is, fluorine, hydrogen peroxide, whatever that is, nitrous oxide, O2 gaseous, oxygen liquid. Yes, Cl2 is chlorine. I was confused because it's all in caps. And generally, yeah. Chlorine is scary. We're using liquid oxygen. There is the option to select from the periodic table, just like with fuel, but I don't think this list pretty much covers almost all of the viable oxidizers. I guess if you were to mix it with some inert thing, I guess like if you mixed it with liquid nitrogen for some reason, I don't know why you would, but you could do that. So we're going to select liquid oxygen and continue. So now here is where the fuel ox ratio comes in. Yeah, so we already have Regen's fuel ox ratio, but I'm just going to put in basically what we did to get this fuel ox ratio. So we started with the stoichiometric ratio, which I don't remember off the top of my head. I want to say it was something around 2 to 3. And we just put in a spread of numbers here. So I'm just going to put in like 1, and then like 1.4, 1.6, 2, 2.4, 3, 3.5. Just kind of a random spread. And then, yeah, I'll show you guys what parameter to look for in the output to maximize the efficiency here. Also, there are other ways you can specify the fuel and ox ratio. The easiest one for the post-processing math is to just do oxidizer to fuel weight ratio. As this helps a lot when calculating the mass flow rates of your fuel and oxidizer. You don't have to go through any kind of mole ratio, although it looks like these are all by weight. So anyway, we just use this one generally. So put those in, accept and continue. And now you can define a bunch of different exit conditions. It looks like these are optional. I think if you want to get an area ratio out, you should probably put something in here. So you can either put the pressure ratio, which is what we're using. You can also use the put in an area ratio, and it will output the pressure ratio. I'm actually not sure what supersonic area ratios is. But anyway, for regen, we picked 55 is our pressure ratio. And we're going to go ahead and accept and continue. And now here is a bunch of different options for the calculations. Generally don't touch any of these. I don't understand most of these, but yeah. Then you submit, and it comes out with your nice.
Do we not want a finite area combustor?
I honestly don't know the difference what this makes. It probably is a better approximation to use finite area combustor. I'm not really sure what is different about the math. I've just never touched these. You can play around with them if you want, but I've never touched them and been fine. So yeah.
Finite area will just change how it calculates equilibrium and stuff. For a first pass, I'd leave it as the infinite area just because the finite area is basically, if we design the chamber correctly, it shouldn't make a difference. The finite area assumes that it will make a difference, and that can be a pain in the ass.
Gotcha.
All right. So once it's finished, it gives you a nice output here, which if you click on these links here, you can get them in a PDF form that you can download. Yeah, so this is what one of the output files looks like. It gives you a whole bunch of things, as I said. So here's like, what is it? This is pressure ratio. So this is chamber pressure, or yes, chamber pressure over whatever the local pressure is. So obviously chamber pressure is 1. Pressure at the exit was 55, as we defined earlier in the inputs. Here's the absolute pressure in bar. Gives you combustion temperatures, gives you density of the flow, all of these thermodynamic stuff that we're not going to worry about. M is, I want to say M is something to do with moles. Yeah, a whole bunch of other stuff that I'm not really sure what this is. And then specific heat ratio. Sonic velocity is something that we care about. Mach number is another thing that we care about. Mach number is basically the ratio of local velocity to the sonic velocity. So if you have these two, you know what the flow velocity is at that point. And then other stuff, the area ratio. So this is the throat area, or exit area over throat area. Some other stuff that I'm not sure about. And then this is the big efficiency measure. ISP is the specific impulse. And basically, the higher this number is, the more efficient your engine is. So if you look, here's another run with a different fuel to ox ratio. So this one's at 1.4, gives us a specific impulse of 2596, which compared to this one, would you look at that, is more efficient. And then 1.6 is even more efficient, and then yada, yada, yada. So yeah, this is a run of CEA. Let me just, if you do this, you have a full page, and then you can download it as a PDF by going to print screen and then, save as PDF and all that. So basically next week, what you guys are going to do during the Thursday session is take what you guys picked on last Thursday, and run the CEA for it. And that's about it. Are there any questions before I do a second example? Does anyone want me to do a second example, or do you guys feel comfortable with this so far? Do you just want to play around with it a bit? That is a good question. Where does it say that? Oh, okay. That probably means whatever. Yeah. Okay. Yeah, that probably means whatever you put in, whether it was the propellant combination or the fuel ox ratio didn't sustain combustion. I mean, that's my best guess. It could be a number of different reasons, but that's probably it.
Jackson, can you run through an example and then get to the uh, OF ratio selection page again, real quick? Or can you roll back to that? No.
Yeah, hold on. Yeah.
So
Here we go.
a decent place to start with this is if you switch to, can you scroll up a touch? Switch to the fee selection. And instead of this will give you an idea of where you want to be. Because what this is the stoichiometric combustion. So if you have a fee of 1, that means that in theory it should burn completely and give you the hottest possible exhaust, which isn't always what you want, but it kind of gives you the location that you want to set up around. So like if you put in 1 for this and then run it real quick.
Yeah.
See if it'll tell you the OF ratio.
Oh, it does.
Yeah.
Yeah.
So that's with the like, if everything burns with everything else perfectly, that would be the kind of ideal. Well, it would result in the hottest possible exhaust, but you wouldn't necessarily want that because sometimes you want like more moles of gas product, which comes with a lighter molecule, which means you want like carbon monoxide instead of carbon dioxide, which is why we use the specific impulse, the ISP, as the actual measure. So you can use this as something to center your spread around and then go off of that to just figure out around where the best specific impulse is, and then just do another pass with like a finer spread of OF ratios.
So once we have like that fee value, is there a way to get the mass flow rates from that?
Yes. Yeah. Well, that is so that we've typed in the fee value. The equivalence ratio is 1 there, right? You see that?
Hold on. Where?
Right there.
Okay, yeah.
And then on the left, the O over F. That's
the mass flow rate one.
Yeah, that's the mass ratio. So we can spec that. It's kind of nice to spec that to be a normal number. So it's just ugly, but there's no reason it has to be.
Gotcha.
You can also just do a spread of fees like 0.8 to like 1.5 or something like that and see what the ISPs change with like that. But again, you would come out with less pleasant mass flow numbers than if you spec it as a mass flow ratio and kind of do the same spread.
Cool, thanks.
Also, I think I want to say for most fuels, the most efficient ratio is going to be fuel rich. So the OF ratio here is going to be less than stoichiometric. I'm not sure why, and I think there might be.
Well, that's for the reason I was just talking about, actually.
Yeah.
Because that if you have less oxygen available, you end up with more of that carbon monoxide, which is a lighter molecule. So you have your molar mass of products on average is lower. And from an ideal gas law, that means you have like a greater resultant pressure and shit.
Yeah. And then for Carrie's question, so phi is basically the ratio of whatever OF ratio you're using to what the stoichiometric ratio is. So in this case, where phi equals 1, your stoichiometric ratio for combustion is this. And then if phi is greater than 1, oh boy, I want to say you're I don't remember if you're fuel rich or ox rich, but this ratio is slightly off in one direction, and if it's a little less than 1, it's slightly off in the other direction. And whatever direction that is depends on how phi is actually defined. I don't remember if it's OF or fuel to ox. There's a lot of ratios to remember, but yeah.
So the other reason that we do fuel rich instead of ox rich is that if you're ox rich, you have you have more oxygen floating around in your hot exhaust, and hot oxygen likes to attack metal, and you're basically going to be rusting away your nozzle at a very accelerated pace. So the Russians actually did ox rich for some of their engines, and it was a bad idea, and they were really unreliable. So that's why we do fuel rich.
So will the amount of parameters we enter ever have a substantial effect on how long the CEA takes to actually calculate?
It's usually on the order of seconds, like 10 to 15 seconds, so not too much.
I don't think you can ever like get it to take more than a few minutes to run.
So we can take that oxidizer fuel ratio and then build our range around that optimal number, right? To make sure it doesn't diverge the sim.
Yeah.
All right, just making sure.
All right. If there aren't any more questions, I'm going to go back and run one for the example ethanol and LOX engine. Yeah, so rocket, and I have right here was our spreadsheet. Chamber pressure, let's see what that is in PSI. 2000 PSI. What a nice number. So we're just gonna put 2000. We'll do 2014.7. Make sure you remember to switch it to PSI if you're doing it in PSI. If you put 2000 ATM, that's gonna be a bad time. Oh yeah, CEA doesn't love alcohols, especially if you use it as an alcohol water mixture. We had some problems, some weird things happen with that over the summer. So here's use periodic mixture since we're using ethanol in this example. Ethanol is an alcohol, so that's CH and O. So ethanol, C3CHO is ethanol. Yeah, this fun fact is the alcohol, grain alcohol that you drink in alcoholic drinks. So we select that. Yeah, over the summer we tried, let's say we were using, I don't know, say vodka or something, which you wouldn't want to use because that's, I think, more water than it is ethanol, or more other stuff than it is ethanol. You could check this box and mix it with water. But yeah, CEA was giving us weird stuff with that. So we're just going to use pure ethanol for this. Liquid propane should be fine. I think most of the hydrocarbons should be fine.
I mean, yeah.
Oh, yeah. You're trying
So
to
it doesn't like liquid propane. That's
it doesn't like liquid propane.
That's surprising.
100% ethanol. We're gonna skip this. We're using liquid ox. Again, you can select anything you want. But it will probably not diverge if you select something that's not reactive, like, I don't know, carbon. OF ratio, I think we also used 1.6 for this. Yeah. Oh, not tab. And continue. Okay, yeah, CEA does do weird things sometimes. I'm honestly not surprised. Oh no, not
Yeah, I mean, if you can't
55.
tell, this entire program is like built on top of a COBOL program, and it's not exactly the most well designed interface. But it is an
Yeah.
official NASA program, which is real special.
It was basically like someone. So I think the real code this is based on is called StanJan, which was
Yeah, I
a
can
joint between
Stanford.
Stanford and the military to just do a basic chemical equilibrium calculator. And then it was probably just like the NASA interns were like, hey, can you take this and turn it into something applicable to rockets? And they did an okay job at it. But it works well enough for what we do. Yes.
The pressure ratio is, again, based kind of arbitrary based on what our feed system can handle. What did you set for this one, Jackson? 272?
I put 272.
Oh, yeah.
This is like almost vacuum, I think. Actually, no, it's not. It's because our chamber pressure is stupid high.
Yeah.
So if you look here, it gives you P bar is we're at half a bar at the exit, and
Bar is basically 1 atmosphere.
yeah.
So
So
7
this is
psi.
basically half of atmospheric, like 8 psi.
And yeah, the engine that this was designed for is just like really big. It's never made for us to build.
Yeah,
It
this
was-
is a purely theoretical engine. I think we picked what our thrust to be. Yeah, 450,000 newtons. This is like approaching actual like orbital rocket scale. This was just a little fun thought experiment.
Yeah. So for you guys, again, it's just kind of like it's really just based on like what the we can supply as a driving pressure. So that depends on like our compressed gas bottle. For a bigger engine like this, it would be based off a turbo pump, but that's still beyond what we can do.
Yeah.
It's not worth considering for an engine we try to build.
So yeah, thrust is not something that this solves for, correct?
No,
Yeah,
because
no.
thrust is linear with your chosen mass flow rate. So you'll see this only gives you your mass flow rate ratio for fuel and oxidizer.
Yeah, and it
Ah.
also only gives you your exit to throat area ratio.
Yeah.
It's
Not your
your thrust
actual
that's going
area
to
or-
correlate the actual mass flow rates to the actual nozzle area dimensions.
Yeah. So where is it? There's the exit. Yeah, actually, so you can see it there. You have the sonic velocity and the Mach number in the bottom line, so that first block. If you multiply those together, you would have your exhaust velocity. And then because of momentum being conserved, you have your thrust is equal to your chosen total mass flow rate and that exit velocity number.
Arun, you're jumping ahead. This is next week's lesson.
Yeah, I know, but like that's where it comes from later.
Okay. And then Joshua, so why would you not want exit pressure to be equal to atmospheric?
That's exactly it. Yep.
Yeah, we are. This one is designed for a higher altitude than atmospheric. So, yeah, for anything that's like fired just statically on the ground, the most efficient engine you would get is if this exit pressure is 1 bar, and then whatever the pressure ratio corresponds with that. For this is just going to be maximum efficiency at whatever altitude, like 8 psi is.
Yeah, that I think they spec that for 20,000 feet.
Yeah, something like that.
The other reason is the lower your exit pressure. We'll get to it later, but like the larger that exit area of the nozzle is going to try to be, and also the longer the nozzle is going to try to be, which means that if you're in atmosphere, suddenly you have to deal with like this massive nozzle and drag from the atmosphere on this massive nozzle, plus the weight. So you really want it to be somewhere around like halfway through the burn on that engine for an actual launch vehicle.
Yep. And then this is pretty much it for this week. We got about 10 minutes left. If you guys want to ask questions, go ahead. Otherwise, if you have no questions, you are free to leave until Thursday.
I also suggest if you have time, just try messing with the with CEA.
What's a realistic minimum pressure to have for our exit pressure?
You cannot get supersonic flow at sea level with less than 23 psi. So that is your absolute minimum.
For your chamber pressure, yeah.
I meant for the exit pressure.
Oh, well.
Exit pressure. I don't actually know. If you get too low, you could break the nozzle and explode. I don't actually have any math on what that is, and it depends on how beefy your nozzle is.
If you're trying to run this at sea level, you don't want to design it for more than like 5 to 6 psi away, or below, because as Jackson was saying, you can break the nozzle because the nozzle will try to like expand the gases out of it, but then they'll start like collapsing back inwards because the exterior pressure is like larger than what the nozzle is trying to expand it to. And you'll actually have the flow break away from the wall of the nozzle, and then you'll have like weird oscillations and shock waves.
Gotcha.
So
How does it not do that at slightly below atmospheric?
It does. It's just that it's not a large enough effect there. Like it doesn't break away until it's already pretty much at the end.
Gotcha.
All right, yeah. As I said, we're pretty much done for today. So if you guys want to peace out, that's cool. Oh, what is this? Oh, yes, the movie night.